test is going to be over Chapter 9 and Chapter 10, mostly. Chapter 9 is just all about energy, how energy works. We barely talk about energy at all this semester so far. But the best place to start for this energy and chemical reactions, to me, is always starting with bond energies. I'm probably going to use a different book next semester, but this one doesn't start with bond energies. It's all the way down in section 9 of chapter 9. But this will give you a good intuitive understanding of where the energy is flowing during the chemical reaction. The first thing I put in the new PowerPoint is this average bond energies thing, table 9.3. Let me go to both. So this is just saying an H to H bond, 436 kilojoules per mole. If I, oh, that screen went on. See if they both come on. Is that one right? Oh, come on. Are they both on now? Go to the page. Of course, so you don't want to memorize this. I'll give you that on the test and you'll need it to answer questions. But let me kind of jump in and just show you what's happening with energy. So let's say a reaction like, I'll do four hydrogens, 4 oxygens, and 1 carbon. Okay, so there's a reaction. This is called a combustion reaction. Okay, and what you have to do is, I will tend to give you these structures, so you're not sitting around trying to make Lewis structures to know what the molecules look like. Double bond to oxygen. CO2 looks like that. We've got 2 H2Os. So this is what we got for reactants, and here's what we got for products. Okay, you have to put energy in to break these bonds. So there's going to be a meaning energy goes in, you have a plus sign because energy is going into the molecules. You have to look at it and decide what bonds are breaking, because it isn't always true that all the bonds are breaking, but for combustion, all the bonds break. So what I've got here is a C2H single bond. I've got 4 of them, so I've got 4 C2H bonds, and I've got 2 4 C2H bonds, and here I have 2 oxygen to oxygen double bonds, and then forming over here is 2 carbon to oxygen double bonds. And here I have 4 H to O bonds. So these are the bonds that break: 4 C to H bonds and 2 oxygen to oxygen double bonds. You follow me so far? When new bonds form, so energy comes out when bonds form, negative. Okay, so let's see what we've got. 4 C to H bonds. I snapped a picture of that big chart. So I'll look here, but you look across the chart. Here, just so you see what I'm looking at. So this tells you the bond, and the thing just to the right tells you how many kilojoules per mole. There's H and C bonds right there. It's the second one down on the left column. We've got 414. Double bond oxygen. Can you see it? There it is. You see it? Double bonded oxygen. Oxygen to oxygen double bond. That's 498. Carbon to oxygen double bond. It's over here. 736. You see the star there? When it's CO2, you see that star right there? When it happens to be CO2, it's 799, not 736. This is 799. And then H to O bonds. There, 464. You with me so far? So since we have 4 of these, we have to multiply that by 4. This is how much energy in kilojoules per mole it takes to break one of these bonds. I have 4 of them. So the total energy is 4. This times this gives us that. It's kilojoules per mole. Two times 498. 996. 799 times 2 is 4 times 464. So it takes this many kilojoules to break all 4 bonds per mole of this. It takes 996 kilojoules going into these 2 to break them. When these form, this is how much energy comes out. So I'll put a negative sign there. And then this many kilojoules per mole to break these 4 bonds. Or no, to form those 4 bonds. Energy comes out when bonds form. Energy is going in when bonds break. You with me? So from there, we're going to add these 2 together. 6 plus 996. I'll say H is just the letter we use for this thing called enthalpy. The technical term for the energy for chemical reactions is so it's just a big vocabulary word. So I'll say delta H energy in, or I could say energy to break. I'll say breaks. Break bonds is and then the total energy to form bonds, the energy comes out is negative 1598 plus 1856 negative. You with me so far? All right. 2652 minus 3454 negative 802. So I got negative 802. What that means is, when you do this reaction, this much heat comes out total from the reaction. When that's negative, we say it's exothermic. Because this is negative, more energy came out than went in. So you had energy come out, and this is typical of combustion reactions. I mean, you've heard of fire, that's combustion, and you know it gives off heat. So that makes sense. Does this make sense to you? It's worth noting, there's a diagram here, I might just draw one. They did a different reaction here as an example. But let me just draw my own diagram here. A total of 2652, this goes into break bonds. We diagram it like this. Goes up. So these reactions are sitting there. This much energy goes in to break all the bonds. And then, so it starts at some energy level. It goes up to here. And then negative 3454. It's negative 3454. And then the distance this goes down below this line is the 802. This is the negative. So those atoms, the molecules that are there, this much energy goes in, this much energy comes out, and this overage going past here, this is the heat that you can feel coming out of the reaction. And it's exothermic because this is negative. There are endothermic reactions. this chart. The larger the number here, the stronger the bond is. Another way of saying it is, if you're breaking a bond, how much energy you have to put into it tells you how strong the bond is. Meaning comparing H to H bond and C to H bond, it takes a little more energy to break this H to H bond than it takes to break a C to H bond. That means the H to H bond is stronger. It's just what you think of as strong. You've got to put more energy in it to break it up, so the bond is stronger. So another way of stating what you see here, need to erase the reaction. If it's exothermic, so those are two facts that always go together. If it's an exothermic reaction, delta H. Delta H for the reaction is negative. You with me? Also true when it's exothermic. The bond is broken, or I'll say as a whole, are weaker than the bonds that form. Here's the total amount of energy it took to break the bonds. Here's the total amount of energy that came out when new bonds formed. These are stronger because there's more energy in this arrow than there is the first arrow. See what I'm saying? These two things are always true. Energy goes in to break the bonds, it's a positive value, and it comes out when bonds form. It is possible, so this is my exothermic. It is possible, the other one is endo. An endothermic reaction, it's just the backwards, the opposite of all of this. Delta H will be positive. Positive. And bonds broken. It's a whole. Does that make sense? And if I drew the chart, it's sort of a starting point. Bonds going in, and bonds forming, and you end up above here. And this is the delta H reaction. This delta H That's the delta H. And in this case, the delta H is this distance. So this one's positive by a little bit, and this one's negative by a little bit. So I could put another reaction up there that's endothermic, and we would go through the whole thing, and we would find out that the delta H is positive. This is endothermic. This one is exothermic. If you wanted a diagram. That makes sense? Okay. Have you worked some of these yourself? Let's look at those. You really need structures for these. So if you had what do I have here? This is plus H2 So really, the first thing you have to do is figure out which bonds are breaking and which bonds are forming. What's going on here is that bond breaks, and there's a single electron floating there. This bond breaks, single electrons floating there. Those two come together, and those two come together to make these two bonds. So we're breaking an H to H bond, one, and here we're breaking a C to C bond, one C to C bond. That we're breaking. Here we're forming two C2H bonds. Go to my chart. H bond, there's one of them, that's 436. C2H bond is 415. So the total energy that's going in, 347 plus 436. So I'll write delta H to break the bonds, 783. Delta H to form bonds is negative 828. So our estimated delta H here is 783 minus 828. Delta H of reaction. So is it endothermic or exothermic? It's exothermic. Are the bonds in the reactants stronger than the bonds in the products? No. The bonds in the products are stronger than the bonds in the reactants. So there's an example. The key is figuring out which bonds are breaking and which bonds are forming. Notice these bonds never broke, so those weren't involved in any of this.
Will you give us a test?
I'll give you the structures,
Okay.
but you'll have to figure out which bonds are breaking and which bonds are forming.
Okay.
And yeah, they don't really give you the structures explicitly, but combustion reactions are really standard. I mean, well, I'll give you the structures, is what I'm saying. Let's do another one.
You just have to be a combustion reaction. Is it more about a combustion?
What about a combustion?
Is it going to be a combustion reaction?
It could be something other than combustion.
Okay.
These types of examples almost always use combustion, but there's examples of endothermic too. I will get quizzes for this one on D2L for these types of calculations. I think I already have some made, I just have to find it. So this one. Happen all. It's this is 80. The one I just did before was 79. So this, let's go to So to be a little more explicit so we can count, we've got 3 CO2s, 3 O2s, and then 2 CO2s, 3 H2Os, so we've got this and all of these. So here, all of these break apart. So that's 3 of those. Yeah, another hallmark of combustion reactions is 6. 6. 7. That is balance. typo. I'm missing something, but we'll take the OH off. That means 2 of those, 6 of those, that's 4. 6, 2 carbons, 4 oxygens, 6 oxygens. I think that's balanced now. 1, 2, 3, 4, 6. Now I have 6 hydrogens. 7. 7 O2s. I'm going to have to come up with some better examples. The motion reactions are the ones that are so hard to balance. Maybe there's another example.
Why was that not balanced?
Huh?
There were 7 oxygens on both sides.
So if I did this again, is that balanced? Oh, I was missing this one. 6, 4, 5, 6, 7. Yeah, okay. That's balanced. Good, good, good. And then 6 hydrogens. Yes. In this case, we have 1, 2, 3, 1, 2, 3, 4, 5, 5 C to H's. 1, 2, 3, 4, 5. You have 1 carbon to carbon. You have 1 carbon to oxygen. And you have 1 oxygen to hydrogen. Those are all the bonds that are breaking. You follow that? And then we have 3 of those. And now forming, we have 4 C to O. Forming here, we have 6 O to H. So now you look at the chart. C to H is 414. C to C is 347 kilojoules per mole. Value from the bottom of the chart. 799. C double bonded to oxygen. This one was 790. O to O. 498. 6 O to H's. H is 464. C to H was 414. C to C, 347. C to O, 60. This one's 464. See what I've done? You guys good with that? So now we have to do the math. 5 times 414. 347, 360, 464. 2070 plus 347 plus 360 plus 464. 3 times 498. 1494. I add those together. 3241. This is kilojoules per mole. Delta H forming. 4 times 799. And then 6 times 464. 784. Add those together. 5180. Kilojoules per mole. So our delta H for this reaction is going to be negative. This 4735. Figure out which bonds are breaking, and then you just crunch all this math. You get an estimate. It's really an estimate. There are ways to measure this for real, and we'll cover that too, but this is one way to estimate the energy of a reaction, the enthalpy of a reaction. I know I have some in my database that are in November. We can take this one. All right. What about this one? Here's the balance. CH4 is this. It is balanced. So again, we have this structure, CH4. Cl2 just looks like that. If you did the Lewis structure, you would have that, but we don't need to fill those in. So you have to look at and decide what's being broken and what's being formed. Only one of these is being broken. Do you see that? These three, at least the way I have it drawn, these three just stay the same. So those never break or form. They just stay how they are. So we just really just have one. We have this breaking. One C to H.
And that's breaking because C in the reaction is going to be chlorine.
Yeah. You have to look here and go, okay, the only thing that's changed is that. So that means that's the only one to play. You've got one Cl to Cl. Forming is one C2Cl and one H2Cl. Chart C to H 414 Cl to Cl 243 C2Cl H2Cl. Four one four plus 243. Times 339 plus 431. 657. I got exactly that. Don't think there's really time to start one of these other subjects. Yeah, I can do this. This is kind of a review because I did start this. Didn't I start this for y'all? And then I just said it won't be on test 2. 6. So also look at 9.6 exercises 56, 57, 59. So this thing about bond energies, also known as bond enthalpies, the reaction is energy of reaction or enthalpy of reaction, just fancy vocabulary. This gives you a good intuitive understanding about what's going on, energy going in, energy coming out, strength of bonds. But you can come up with an estimate, but let's assume no one estimated this, one actually measured it. It's called calorimetry. It can be done. And the way you'll see it is A02, that's typically the one we just calculated. I think you got 802 when you did it. But if you have this, in hand, (2O2, CO2, 2H2). If you have that in hand, balance that right, CO2, H2O. And then you've got this that says, delta H of reaction, that thing we just spent our time estimating, negative 802. They write these in kilojoules, but it means kilojoules per mole of this. Books aren't generally very clear about that. But it's kilojoules per mole of CH4. The moles is the CH4. But you'll remember this, if I did go through this for you before. This is just like before where I told you that this is a summary of 1 mole of CH4 to 2 moles of O2. That's 1 mole ratio. You've got 1 mole of CH4 to 1 mole of CO2. So there's that relationship, 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 there's that relationship. There's really 6 relationships like this in there. You remember me telling you that? Similarly, when you're given a reaction, a balanced reaction, and you're given this, what it means is negative 802.3 kilojoules for 1 mole of CH4. That's one of the relationships that's here. Another one is negative 802.3 kilojoules to 2 moles of O2. Negative 802.3 kilojoules to form 1 mole of CO2. So that's that one. And the last one is negative 802.3 kilojoules to 2 moles of H2. So when you're given this, in addition to those other mole ratios, you have those summarized there as well. You follow that? You guys follow that? Okay. So what you can do with it, if you're given that, what mass of CH4 must you burn to get 325 kilojoules of heat? We're referring to the CH4. Burns to get 325 kilojoules. And this is 56. I think I'm doing 56 right now. All right, so I'm going to use this mass of CH4. Since mass of CH4 is mentioned, we've got moles here. We're going to need carbon. There's 1 atom. Hydrogen. There's 4 atoms. 12.01 off the periodic table. 1.01 off the periodic table. 16.05 grams per mole for CH4. So you see what I just did there? That's a review as well. You guys with me? So we're going to need that. So what are we given here? We're given 25 kilojoules. Put that over 1. I'm going to use this next because I need kilojoules on the bottom. Negative 802.3 kilojoules for 1 mole of CH4 and 1 mole of CH4 weighs 16.05 grams. That'll do it. That'll tell you what mass of this you need to put in and burn to get this many kilojoules. This was given in the problem. This was given in the reaction there. And then I got my grams per mole the way we typically do. And I get our answer here. So this is really more simple than
Can there be a quiz on your screen?
yeah.
So that,
Yeah. All of these things I can make quizzes out of easily. I think I have a database of these. Part of my problem is I lost a bunch of my database from UNG. Don't know what happened to it, so I think I have these though. I'll look for them. What am I doing? 325 times 16.05 divided by 802.3. I guess I want 3 significant figures. Oh, you generally just take the absolute value of this, because there's no such thing as negative 6.50 grams. You guys understand that?
yeah.
So check those out. I will get some quizzes up, but if you want a little practice on some of this, you can look at